blinking. We are on. All right, now. All right, so now let's do the second part. Okay? Okay. Now, anybody want to tell me what to do now? Notice it says instantaneous. Yep, got to take the derivative, don't we? So our function was what? Now this is part B. The function was 4 centimeters plus 2.5. Yeah, 2.5 centimeters per second squared. I always like to go back and rewrite it, and that's t squared I plus 5 centimeters per second. 5 centimeters per second. What? J. And that was, getting in a hurry. I don't know why I get in a hurry, but I do. All right, T, and then that's J. Okay? So we take the derivative, don't we? Well, that's easy, isn't it? Okay, so R becomes V. R becomes V, right? Anybody want to tell me what it's supposed to be? Now this term right here is not going to change, is it? Oh, excuse me. What's going to happen to that term? Ooh, yeah. Boy, I like to goof. All right? Because it's a constant, right? Because it doesn't have a T on it. All right, now, what's my value going to be? Anybody want to tell me? Okay. So let's just do it first. 5 centimeters per second squared T I. And what's my J term going to be? Yeah, you got to leave the units alone. Mm-hmm. No, you don't mess with the units. All right, what's my next term going to be? Just 5 centimeters per second? J, right? All right, now, what does that tell us about the J velocity vector? Very good. It's become constant, hasn't it? It's not changing anymore. That's right. Very good. Dang, y'all are good. All right, that's good. I usually have to stress that to everybody, but y'all got it right out of the box the other day. Yeah, go ahead.
And that's the instantaneous velocity?
That's the components. That's the components. But now what will it be at time 0? So there's not an I component, is there? So we're going to write it this way. At velocity at time 0, because see, you got to go ahead and plug the times in. Okay, so at time 0, what's it going to be? Well, and look, if you want to go ahead and write it this way, you can. Probably wouldn't hurt. It's going to be this, isn't it? Because look, when you multiply 0 seconds times second squared, it becomes seconds. You cancel the units, and it becomes that I, and we're just no I, plus what? Yeah. And that's at time 0. All right, now what's it going to be at time? Was it 2 seconds? Oh, 1 second. Oh, it was. Okay, my bad. All right, so at time 1 second, what does it become? It becomes what? Yeah. Mm-hmm. Very good. So you put a 1 in here, and so we got what? 5 centimeters per second squared. Now watch. And it's times 1 second. Now watch. Cancel, cancel. Plus 5 centimeters per second J. And so that becomes this, doesn't it? It's 5, oh good grief, 5 I plus 5 J, right? Right? Okay. Now that's the what? The instantaneous velocity. But now we're not, look, but now are we done? We got to do it for what? 2 seconds also? We got to do it for 2 seconds, all right? So V at T, we got to do what? Squared times 2 seconds plus, and we know that's not going to change. And so V at t, 2 seconds, it becomes 10. So let's do this now. So that's going to be 10 centimeters per second, I, plus 5 centimeters per second, J. Okay, then we got to do what? It says find the magnitude and direction, right? Okay. So we got to do what? Square root of the squares. Okay. But it's what? It's the final and the what? It's this one and what? And this one. Right?
Yeah, you gotta find
You gotta find each one
it at each
separate.
one. It's what it's asking for.
Oh, it wants it.
It says, what's it at?
Oh, it does, don't it? Okay, my bad. All right. So what is it going to be at this one? We do the square root of the squares, right? Be what? Well, 0. That's 0. Plus what? 5 squared? I misread the problem. And so that's the square root of what? 25? Which is 5. Right? And then at times 0, what's it going to be? Or excuse me, time 1. Well, it's the same thing as that other one, right? What was that, 7.08? Was it 7.07? And what is it right here? We got 10 squared plus 5 squared. And let's say that's 100 plus 20, that's 100, square root of 125 is what, 11.2? Yeah, 11.18, okay. I rounded, 11.18, all right. Okay? All right. My bad, I misread it, okay. All right. Okay? All right, now the direction. Okay? Well, we want to go with the last time interval. Okay? All right? So let's look at the last one because that's final, okay? That's what we have to go by. Or we can do it for each one. We can do it for each one. Let's just do it for each one. What would it be for this one? What would it be for this one? 90 degrees? Is that right? Oh, shoot. Tangent. And that's going to be what? 90 degrees? Because what? Y is what? Our X is 0. Y is 5. So, yeah. So that's 90 degrees. What about this one? Arc tangent. Let's see. We've already done this one, hadn't we? It's 45. And then this one's what? Arc tangent. Let's see, it's going to be 5 divided by 10. What is that, 20 what? 26.6? Yeah. Okay. Now, y'all, I'm not going to give you a real long one like that. I mean, I might ask you the first part or something on the test because that's long. Okay. But can you do that? Do you feel comfortable doing that now? Does that make sense? A little bit? I'll admit now that one's challenging a little bit. It's a little bit, okay? It's a little bit challenging because, again, what did we start with? We started with R, but it wanted velocity. Now remember what I said about R. R means it's both I and J. So you got to subtract your components. You got to do your components. Oh, okay, sorry. Yeah. And let's just keep everything on the screen. I'm not going to write on the board anymore. That way it's up there. Yeah, and you will, but yeah, tangent's undefined there, yeah. Yeah. Okay, all right, that's a good question. How do we know it? All right, I lied. I said I'm not going to write on the board. Okay. All right, arc tan, and I'm going to show you, watch. All right, we said y was 5. That means x is 0. All right, let's graphically think about it. Where's x 0? Right there. Where would y be 5? Somewhere up here. 90-degree angle. Does that make sense? Yeah. That's why I always like to draw stuff. But like you said, it's undefined. You know, you can't, how do you, it's going to give you a math error. Yeah. But it's real. I mean, it's there. Yeah. Look at your numbers. Okay. Okay. Right angle. Very good. Very good. Okay? Does that make? That's good. All right. Hopefully we got that cleared up. Okay. Let's see. We did 1. We did 3. We did 5. You know what? Number 4. Let's see. Let's look at number 4. Because that answer is not in the back of your book. We did that in class, though, didn't we? Did I do Shirley Squirrely on the board? No, he's running in the park. He's not on a limb. That was on the tree limb, yeah. This is a different Shirley Squirrely problem. Okay. All right, you want to take a stab at number 4? All right, now look, it's similar. Okay, but listen to what it asks. I'll move it right. Let me minimize right here. Okay, let me pause. Right. Okay, I'm glad that's not on video. All right now, and everybody's gonna wonder what did he say? Okay, so anybody want to give me what it's supposed to be? I mean, we just take the. Let's see. Did I write it down? I did write it down, didn't I? No, I didn't. Okay, so we're on what? Number 4, and so number 4, it was r is equal to what? 0.28. Was it meters? Yeah, meters per second. And I know I didn't draw it, but let's see. It was meters per second. What? Yeah, t. Okay. Plus 0.036 meters per second squared t squared. And of course that's I plus 0. I'm running out of room. 0.019 meters per second, and I think that's cubed. All right, t cubed j. All right, we just take a first order derivative, and what's it come out to be, y'all? It should come out something like what? For the x, let's do the x first. All right, for the x component, it's going to be what? Well, that becomes what? 0.28 meters per second. Let me put a brackets there. Plus, what is 2 times 0.036? 0.072? Yeah. So let's go ahead and multiply it through. It becomes 0.72, 0.072, right? Meters per second squared, t, I, plus, whoops, I said let's just do that part first. Now let's do that y component. The Vy is going to be what? It's going to be what? 3 times 0.019 is what? Well, 19 plus 19 is what? 38 plus another 19 is what? 48, 50, what? 50, what? 7? I can't count today. Yeah, 57. So it's going to be 0.057. And that's meters per second cubed. Gummit. Meters per second cubed. And that becomes what? T squared J. So there it is. There's your components. Okay? And of course we could write it all together. Be fine. All right? Now, what about B part? Has anybody looked at B? They've already done the B part. What was B? At time 5 seconds, how far is the squirrel from its initial position? Okay. Anybody want to tell me what to do? Okay. All right. I think y'all are all, yeah. Use the first one, right? Is that what everybody's saying?
I think it's.
Notice, let's read it again now. That's what y'all said, didn't you? Find the, now hang on, let me make sure I read it right. What are the, all right, X and Y components, okay, we did that. At time 5 seconds, how far? Displacement, right? Which is what? R or V? R. And that's what you said, you said, you said. I think we all said. Are we good? Now, what if it has said, what is the velocity at time 5 seconds? 5 into the velocity derivative, right, where we took the derivative. Everybody understand that? Okay? Okay. Is this starting to clear up the fog a little bit on some of these? A little? Okay. Okay? I hope. Okay? So let's just plug it in, all right? I mean, it's, we just plug it in. So what was it? It was, God, it was a huge thing, wasn't it? Oh, man, I need to write small, don't I, and neater. Yes, neater, please. All right. 2.8 meters per second times, what, 5 seconds? Well, that cancels out the seconds plus 0.036. Y'all don't let me goof up now. Squared times what? 5 squared. Well, that cancels those out. Squared and squared cancels out. Plus, and of course that's I, that's all I, plus 0.019 meters per second cubed, and it works out beautifully, 5 seconds cubed, and that's J. And so cancel, 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 so we're all in meters, so that's perfect. Cancel that square out. Now when I mark that square out, please don't understand that doesn't mean we don't square it. Maybe I should mark them out. I don't want to confuse you. It just means that the seconds become squared and the seconds become cubed and they cancel each other out there. Okay? Okay. And we get an R of what? Good grief, what an answer. R is what? The final R in the X is what? So we get this, 2.3. It is meters, right? Yeah, meters. I plus what? 2.38 meters J. Is that what y'all got? Now double check me. Yeah? Okay, now that's the what? That's the components, right? Yeah, X and Y, okay. But it's asking for, did it say magnitude? Okay, that's part C, isn't it? Okay, okay, hang on. All right. At time 5 seconds, how far is the squirrel from its initial position? Okay, now, whoa. Yeah, it wants total distance or from the origin, so we got to do what? And I think you said that a minute ago. Yeah, you said that a minute ago, didn't you? So we got to do R, don't we? Right?
That's the part.
That's, no. That's the, it's, yeah, because it says how far. Uh-oh. Now I want to clarify that. All right, let's go ahead and write this down. Let me show you why we have to do this. All right, remember, and I know I didn't draw. I've been breaking my own rules. I'm sorry, brevity's sake, but really we shouldn't do that. It says how far. Okay, if we were to graph this, okay, it would be 2.3 in the X, which is going to be about right here, and 2.38. No, not much farther. Up here. That's going to be how far out on the X, and that's going to be how far. But we don't want to know X and Y. It says how far. Well, it's wanting to know that right there. It's wanting to know the distance from the origin. And the only way you find that is complete the triangle, right? Square root of the squares. Pythagorean. Because look, that's a right triangle. Very good. All right, and then we get what? 3.31? Now part C is what? Do I need to go back? Let us look at it. Let's go back and look at it real quick, because we may not have photographic memories. At time 5 seconds, what are the magnitude and direction of the squirrel's velocity?
So now we plug it into the radius.
Now we go back to part A and do what? Like you just said, like y'all are mumbling, right? I think that's what y'all are mumbling. I think that's what Sarah said, and that's what you said, Juan, and y'all are saying up here. You did say it, right, Sarah? You didn't? I thought you did. Okay. You were saying, I wished I could go home? Okay, all right. Here in a minute. No, that was being nice, right? Okay, no, okay. All right, here we go. So we plug it in, don't we? Does everybody see what we do now? We plug it back into our derivative. Yeah? And then do what? Well, our derivative was what? And that sucker was long, wasn't it? So part C was what? I'm going to write the whole derivative. So it was, once we took it, it was 0.28 meters per second times t. I thought oh no, that first one didn't. I'm sorry. It was my plus I was looking at. Plus, and then it has what? Yeah, it should have in a couple of places, a t and a t squared. 0.0 what? 72? Quit. Meters per second, and that should be what? Squared, t, yeah. Okay, there's the t, and that's I, plus, and then what? 0.057 meters per second cubed, t squared, j. Now plug time 5 seconds into that. Man, these are long, aren't they? Good grief. Plus 0.072 times 5 seconds. Forgot the units. Oh well, and that's I plus 0.57 meters per second cubed times what? 5 seconds squared. And so we should get this for our components. Let me make sure I look at them right. All right. What the heck? Oh, yeah. Yeah. 0.64 meters per second I plus 1.43 meters per second J. Now we got to do what? Yep, very good. Why do these things have to be so dang long? All right, plus 1.43. And let's say velocity, which is magnitude, is equal to, what'd y'all get? 1.57? Yeah, okay, close enough. Yeah, I'll count that. Now we got to do what? It says direction. What do I do now? Arc10. And we get what? Okay. 65.8, 65.9, okay. 8, 9, okay. Either one. I'll take either one. I had 9, okay. Very good. And so in the final result, it looks like this. Both are positive. Notice the X is very low. The Y is very high. So it's going to be something like that right there, isn't it? And so that is a 65.8 degree angle. Okay, makes sense? Yeah? Okay. All right. All right, what about number 6? All right, let me pull it up. I'm on pause. All right. Okay. Where are we at? Click, click, click. All right. What is this, number 6? Okay. We got a what? We got a doggy running. All right. Woof. All right. There's his dog. All right, now. I know it looks like a cat. All right, whatever. All right. Teeth. All right, now. Okay. All right. And he's running. And in an open field has components of what? Well, it says Vx is what? 2.6 meters per second. And Vy is negative 1.8 meters per second. All right? All right. Okay? For the same time interval this is at time 10 seconds. All right? To 20 seconds. But this is at time 10 seconds. All right, now, the average acceleration of the dog is what? So at time 20 seconds, acceleration average is 0.45 meters per second squared. All right, now, at 31 degrees. At 31 degrees. Measured from counterclockwise, all right? At time 20 seconds, what are the components of the velocity? Okay? So we want to know V final, X, and Y. Right? Okay. Now, yes? Sure, uh-huh. Okay. All right. Okay. Well, we don't have them, so we got to find acceleration components, don't we? Well, X is what? Cosine. X is what? 0.45 meters per second squared times cosine of 31 degrees. And that's going to be 0.39? Yeah, approximately. And then Y, 0.45 meters per second squared, sine 31, and that becomes 0.23 meters per second squared. And that's I, and that's J. All right, now, if you want to get technical. Okay. All right, now here's where the kinematics can become very useful. V final is equal to VI plus AT. Now, y'all listen. Just because that doesn't say I and J in that equation doesn't mean it can't be used for I and J. Because it can. All right. So, V final, components, well, the components initially were 2.6 meters per second minus 1.8, and that's I, minus 1.8 meters per second, J, plus, we plug in our components now of acceleration, and it's 0.39 meters per second squared, I plus 0.23 meters per second squared, J. Now we got to multiply the time in there. Okay, do this. Brackets times 10 seconds. Okay? I run out of room. So you multiply 10 times everything in that brackets. Okay? And then you add like terms. Well, oh shoot, really? When you add like terms, you run out of slides, and we got to add some more. So velocity final is equal to, 6.5 meters per second I plus, negative, excuse me, negative 0.5 meters per second J. And there you go.
It's positive.
It is positive?
Yeah, once you accelerate on the Y, you get positive.
Oh, excuse me. It is positive. I thought I had a negative in there. Thank you. Oh, man, I got to get these glasses adjusted. All right. That looked like a negative at first glance. Sorry about that. Okay. Now, look at part B. Part B says, what are the magnitude and direction of the dog's what? Velocity. Okay? Well, okay, y'all. What do we got? Yeah. Or R, V, R, whatever. All right, we know we're doing magnitude, square the squares. Right? And we get a what? 6.52? Yeah. All right. And so this dog was what? Way out here like this, isn't he? But he started out what? He started out in what quadrant? In the fourth. But his acceleration was positive. Let's go back and look at that real quick. He started out, say, look, it was positive acceleration, but he started out, his Y was negative. Okay? So he was actually in the fourth, and now he's crossed over and he's in the first. Okay? And that makes sense because the acceleration is positive, and again, in the X direction, so that makes sense. Okay, that we would cross over and go into the first. All right, now, what is my angle? Well, arctan, isn't it? And you get what? 4.4 degrees? It's a real low angle. Right? And then what's the next part? Sketch the velocity vectors. Well, we just did that one. That's the last one. What would be initial one? This is V final. What would be V initial? Well, okay. We were negative 1.8 and what? 2.6 in the X. So it's going to be something like that. Maybe something like that. Close. This is velocity and time. Well, excuse me. No, I don't know why I'm doing that. My bad. X and Y. Excuse me. Excuse me. Actually be meters and seconds. Yeah. Okay? All right, everybody agree with that? Okay. Now that one, that one was kind of hard. That one's pretty hard because, it kind of threw you a curveball. It's like, well, wait a minute. How do we find the component? Well, you take your magnitude of your acceleration and your direction and find the components of it, and then look at your kinematics. So let me say this again. Your kinematics will apply to these component problems. They don't just go away. They are still there. They still apply. Y'all, we can use kinematics all the way through the rest of the semester. And we will at times. Even when we're doing energy calculations. We may have to go back and do a kinematic. Okay? All right. Okay. All right. Y'all want to work any more? You want to do one more maybe? We've been an hour and 15 minutes. We can go full 2 hours if you want to, and I don't care.
What would X and Y axis be labeled on those? Is it time and velocity?
All right, since it's the magnitude, since it's the magnitude, we're looking at the magnitude of the velocity, and those are the components of the velocity vector. We're looking at the velocity in the X and the Y direction. What would that be labeled?
If you plotted velocity along the x-axis, velocity along the y, it'd be velocity versus time.
Yeah, if you plot velocity versus time, you get acceleration.
The slope of that graph would be
The slope of it, yeah. Yeah, we would we would probably plot it as velocity versus time, yeah. Y would be velocity and time would be on the x. Yeah. Okay. Okay. Good question. Okay. All right. All right, now we've done what? 1, 3, 4, 5, 6. My Lord, we about done them all.
Got it, save some for us.
Say something for y'all?
Yeah, save some for us.
Okay.
Take it to the house.
Take it to the house. Y'all don't want to do a projectile problem? Did I do one with y'all the other day? Oh, y'all sound real enthused. All right. Huh? Say do one. Number 9. Good grief, that's a long one. All right, we can do that one. All right, let's look at number 9. Now, let me say again, do y'all see what we did on that problem? We found the components. Remember what I said chapter 1? Y'all, we are going to use that. We're not going to walk away from it after chapter 1. We will use it all semester long at times. Okay? At times, we'll have to come back to sine and cosine and, okay? But now I'm going to tell you, this arc, tan, and square root of squares, we're going to use it for force. I mean, we are. We're going, when we get to force in 2 different directions, y'all, we're going to be doing it. Square root of squares, arc, tan. Okay? Okay. All right, look at number 9. Oh, yeah, you can't see it. My bad. All right, where are we? All right, Doug, take it to the house. All right. Round them up. All right, now. All right. All right, this is a typical physics problem right here. A book slides off a horizontal tabletop with a speed of 1.1 meters per second. We had a slide this morning, y'all, that matches this perfectly. The ball being shot out of the projectile launcher, this matches this perfectly. Okay? It strikes the floor 0.48 seconds. Notice it has a, now I hope you're listening and looking, a horizontal. So what does that mean? Velocity in the x. And once it comes off the table, what does that velocity do? Stays the stinking same. And what is my acceleration in the x? See if you was listening today. 0 because it's constant velocity. Okay? Now y'all, I'm kind of helping you start this problem. What is my initial y velocity? I mean, just as it comes off the table. I mean, just right there. 0. What is my y acceleration? Always. Negative 9.8. Okay. All right. Ignore air resistance. Boy, that's wonderful. All right. Find the height, which is y, of the tabletop above the floor. Okay. All right. So, now, what are we going back to here? Are we using components here? No, not yet. So we're going back to our kinematics, aren't we? All right, what is initial y? Huh? No. Well, okay, remember, to the floor is going down. So we're going to start at where? What? We could actually flip this either way. But since this is where the motion is, this is initial, let's let this be what? 0. Now, can we flip it around the other way? Yeah. We can let that down there be 0 and let this be final. Okay. Doesn't matter. All right. But let's let this be 0. Since that's where the motion began. Okay. Inertial reference frame. Okay? All right. What kinematic do you think will fit, y'all? You only got 4. Okay, y'all. There's only one force that's acting on this thing. Well, actually, we can call it a force. Gravity. So which one of our equations is going to fit perfectly? That has gravity in it and has something else. It gave us, what else did it give us? What else did it give us in that problem that's very important? It did give us initial, but now, no, wait a minute. That's horizontal. So is that important? All right, is the floor out horizontally or is it vertically down? It's vertically down, so is that horizontal velocity important right now? Mm-mm. Because the book goes that way. It don't go that way. It does just briefly, but it goes zoop like that. All right? There you go. Very good. All right. Now look at your kinematics that has time and has what else in it? And what else? What are we looking for? We're looking for distance to the floor. Delta y. Or we can say y final. Because y initial is what? What? Zildjian, yeah, 0. Okay. No, we're not playing the symbols. All right, now, that's good, wasn't it? Not really. All right. Yeah? You got it? I remember now, y'all have those kinematics handy. Have them on a cheat sheet or something. Okay? Okay? So we're going to use what kinematic? All right, again, what do we need to do first? We need to draw it, don't we? You want me to draw it over here on the board for you? Well, I'm going to help you out here. Did I pause this video? I hope I did. All right. I don't know if I did or not. I don't know. I better pause it. I may be burning up a lot of time. No, I didn't. You're not convincing me. Okay. All right, y'all. I drew it. I'm not going to draw it again. All right, now look. What number is this? Number 9? Yeah. All right, so we know then that what? 9A, it says, how far was it from the floor, right? It strikes for ignoring, find the height of the tabletop. Okay, all right, well, y is equal to 1/2 gt squared. And why is that? Because y final, we got 0 meters plus, all right, what was the initial velocity? 0 meters per second times what? 0.48 seconds plus what? 1/2, negative 9.8 meters per second squared times 0.48 seconds squared. And we wind up what? Y final is equal to 1.13 meters. Everybody agree? Now see, if you'll draw it, you'll label it, and you'll say, oh, hey, that's in the Y. Look, 0, 0, boom. That's all I'm left with. Okay? But there's my final equation. Now, I didn't write a negative. Okay, write a negative if it makes you feel better. Okay? Because in a sense, mathematically, our point of origin, our point where we started is up here. Going up is positive, so therefore, since this is my origin point, then going down would be negative. Okay? No, because it said what is the height of the table? And height is not down, it is what? Up. So let's go back and do this. That. So let's have enough physical sense to know when it says height, height is above the ground. Now, are there buildings down in the ground? Yes, but this is not the case. Okay. It didn't ask how far below the ground is it. It says height. Height here is above the ground because it's a table. Very good. But had you left it negative, okay, you'd have said height of the table. What the heck's going on my phone? Was that your phone? All right, that's your phone. All right. Okay. Oh, my phone's going up right now. Okay. That would have been fine. Okay. What about the second part? The horizontal distance. Oh, okay. Good. All right, y'all. What are we going to do for this one? Yeah. 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 Can we use the same equation except x? Or just, actually we don't even need to use that equation. Just use what? Yeah, time and the velocity. Because the velocity average is what? Yeah. And so velocity is found by what? Displacement divided by the time. So therefore displacement would be velocity times time, right? So we could actually do what for this equation? Now this is not necessarily one of our kinematics per se. Remember we found velocity average is what? So what? Delta x is what? V average times the time. Or we could use another equation, our x final kinematic, and what happens to the acceleration part on that one? It becomes what? If I was to use what? If I was to use this equation to find this one, what happens to this part right here? What's acceleration in the x direction? 0. What is my initial x displacement? We didn't write that one down. Y'all should have called me on that one. What was, all right, look. If we're starting at the origin, x and y, if y is 0, guess what x has got to be? Yeah. So that term's gone. So we're left with what Justin was saying, x is equal to the velocity times the time, which is the same thing as that right there in a nutshell. Did you see how I did that? See, there's more than one way to look at these. Okay? Okay? So, now, Ms. Shields, do I have to do all that? No. Just do it the way that's the easiest way and solve it. All right, y'all, so plug it in. So, x final is equal to what? Well, let's go right here. 1.1 meters per second times what? 0.48 meters per second. You know what why did I write that? Seconds. Dadgummit. All right, you know what I meant to show y'all something this morning. Anybody ever seen the Shoot the Monkey video in high school? Okay, I'm going to show you that before we leave. But I meant to show y'all that this morning. I had it pulled up and I forgot all about it. Okay? All right, and we get what? 0.53. Okay, now look, y'all. All right, look. If I release two objects, and I'll try to demonstrate this later this week or first of next week. If I release two objects from the same height and I push one off the table and project one out at the same height at the same time, are they going to hit at different times? If they're from the same height. If I roll a ball off and shoot one out of a projectile launcher, instantaneously, will they hit at different times? Okay, let's see. Let me ask you this. What if I'm shooting at something and I'm aimed at it, or with a bow and arrow, and I say, and I'm aimed at it now, and I say, okay, you're going to release this, and I'm going to shoot when you release it, I'm going to release my arrow, and I'm still going to hit it. We release them at simultaneous times, and I'm aimed directly at it now. Am I going to hit the target?
No.
I'm not? Okay. All right, let's see.
There's an X. Like if you're pushing on the table, there's one is just straight down. Another one has X.
Okay.
So it takes.
Okay. All right. Well, keep that in thought. Keep that in thought. Let's finish this problem because I almost forgot we didn't finish this problem. All right. What about the last part? The horizontal and vertical components of the book's velocity and the magnitude and direction of its velocity. Okay. Did anybody do that? The horizontal and vertical components. Yeah. All right, y'all. We've already actually done that. What is going on with my marker? All right. All right, so, well, I reckon she's not going to work anymore. So, I'm going to have to do it over here on the board. I'm going to stop the video.